Welcome back, students. This is the lecture number 5. The topic which is going to discuss, that is the refraction of light and refraction of light through a glass slab. Okay, so here you can see the figure. Here we have one rectangular glass slab. Okay, ABCD is your rectangular glass slab, and this Mn is your incident ray. This is your normal, and N dash will be your normal. Okay, so if the thickness of this glass slab will be is small t. Okay, so this is your rare medium and this is your denser medium. This is air, this is glass. So refractive index is mu a for the air and mu g for the glass. Again mu a for the air. So our ray of light coming from air to glass and again from glass to air. Okay, so when the incident ray when incident ray Mn coming at the point of incidence, this is your refracting surface AB. So it after refraction it bends towards the normal, little bit bends towards the normal. This is your angle of incidence I1, this is your angle of refraction R1. Okay, so on applying Snell's law, what is the relative refractive index? A mu g is sin I1 upon sin R1 according to the Snell's law. This will be your equation number 1. Again at point K, the refracted ray travels from denser medium to rarer medium, so it bent away from the normal. Okay, away from the normal. So this will be your angle of refraction, the angle of incidence, and this will be your angle of refraction. Okay, this will be your refracting surface, that is CD. Okay, so again at point K, mu g into sin I2 equals to mu a into sin R2, or G mu a, relative refractive index, G mu a equals to mu a upon mu g equals to sin I2 upon sin R2. This will be your equation number 2. Okay, clear? According to the principle of reversibility. Okay, principle of reversibility which we have discussed in the last lecture. According to the principle of reversibility, for the reversed ray, if I put mirror in front of this refracted ray, the ray will be returned back following the same path. Okay, according to the principle of reversibility. Okay, so for the reversed ray, mu a into sin R2 will be your angle of incidence. Okay, equals to mu g into sin I2, and sin I2 will be your angle of refraction. Okay, for the reversed ray, or mu g upon mu a equals to sin I2 upon sin R2, also called a mu g. This will be your equation number 3. Now multiplying the equation number 2 with equation number 3. On multiplying, we get sin I2 upon sin R2 into sin R2 upon sin I2 equals to G mu a into a mu g. Sin I2 will cancel out, sin R2 will cancel out each other. So we get G mu a equals to a mu g equals to unity, or a mu g equals to 1 upon G mu a. Okay, by the principle of reversibility. Now from equation number 1 and 3, equation number 1 is what? Equation number 1 is sin I1 upon sin R1, okay, equals to a mu g. And what is your equation number 3? Equation number 3 is sin I2 upon sin R2 equals to a mu g. The right hand side of both the equations will be are same, then right hand side will also be same. So sin I1 upon sin R1 equals to sin R2 upon sin I2. I2 and R1 both are the alternate angles. Okay, for this see the figure. Okay, so taking sine of both the side, sin I2 equals to sin R1. Okay, so from equation number 4, sin I2 is equals to sin R1. So put sin I2 equals to sin R1. Okay, so after putting this, we get sin R2 equals to sin I1, or if I take inverse of both the side, we get R2 equals to I1. Okay, this is the normal mathematics which we have used here. Okay, you know about the inverse trigonometry rules. Okay, so there is no confusion is in your mind. Okay, hence the emergent ray KL is parallel to the incident ray MN. The incident ray is displaced laterally on suffering two refractions through glass slab. Okay, okay, next one is the lateral displacement. Okay, lateral displacement of light ray. For this, draw one perpendicular from point K. Okay, that is KL dash perpendicular to MN. See the figure, KL dash, okay, perpendicular to MN. This will be your MN. If I extend this, okay, so this will be your MN, and this is your this is your perpendicular. Okay, so lateral displacement of the ray on passing through the parallel slab KL dash, lateral displacement is what? Lateral displacement is your KL dash. Okay, so in how much amount your ray will be reflected. So you can see here, this ray will be deviated through its original path having angle delta, small angle delta. Okay, so angle K and L dash. What is K and L dash? This will be your K and L dash. This angle will be your delta. Okay, deviation on first refraction. Okay, so in triangle NKL dash, okay, this will be your NKL dash. Here we have to find the value of sine delta. Sine delta equals to KL dash upon NK. You know the trigonometry. KL dash is your perpendicular and NK is your hypotenuse. Okay, so KL dash equals to NK sine delta. This will be your equation number 5. Next one is triangle N dash K. What is which is triangle N dash K? So this is your N, this is N dash, and this is K. Okay, this is your acute angle R1, this is your hypotenuse perpendicular, and this is your base, and this is your perpendicular. Okay, so in this particular triangle we calculate the value of cos R1, that is base upon hypotenuse, and N dash is your base, and NK is your hypotenuse. Okay, so NK is what? NK equals to N dash upon cos R1, and N dash is what? N dash is nothing but the thickness. Okay, N dash is nothing but the thickness. Okay, thickness of the glass slab. So T upon cos R1. Okay, now from equation number 5, here we have KL dash equals to NK sine delta. So KL dash equals to NK. So put the value of this NK equals to T upon cos R1 in equation number 5. So KL dash equals to T upon cos R1 into sine delta. This angle delta can be written as I1 minus R1. Okay, see the figure, I1 minus R1. This you can see from the figure, I1 minus R1. Okay, so KL dash equals to T sine I1 minus R1 upon cos R1. This will be your lateral shift. Okay, or lateral displacement, equation number 6. Okay, this lateral shift can be considered with the help of one example. Here we have one example. Suppose that a ray of light is incident at an angle of 60 degree, okay, on one face of a rectangular glass slab of the thickness of 0.1 m and refractive index of 1.5, and we have to calculate the lateral shift produced. Okay, so here we have I1 equals to 60 degree angle of incidence, T is the thickness 0.1 m and the refractive index is 1.5, so mu equals to sin I1 upon sin R1. So sin R1 equals to sin I1 upon mu sin 60 divided by 1.5, so sin R1 equals to 0.5773, or taking inverse R1 equals to sin inverse of 0.5773. So 35.3 degree is your angle of refraction. What is the lateral shift? Lateral shift is T into sin I1 minus R1 divided by cos R1. So T is your 0.1, I1 is 60, R1 is 35.3. So 0.1 is to sin 60 minus 35.3 degree divided by cos 35.3 degree. So we get 0.1 into sin 24.7 degree divided by cos 35.3 degree, or 0.1 into 0.418 divided by 0.816. So lateral shift is what? Lateral shift is 0.0513 meter. Okay, so this is your example based on this particular derivation.